Alrighty, let's talk about LeChatlier's principle. This is a good one. This has to do with the shifting of the dynamic equilibrium in response to things that might be happening to a reversible reaction that is in equilibrium. But the thing to remember first is that dynamic equilibrium only happens in a closed system. So, you know, if you're introducing other chemicals or changing the conditions and things like that, that means that you're going to affect the closed system, and it's going to throw things out of whack in terms of the equilibrium. Sorry about this long paragraph here, but if the system gets opened up to new, what we call stresses, those stresses include adding and removing reactant or products, or changing the amount of the chemicals present. Another stress is a change to the pressure or a change to the volume in which the reaction is taking place, or a change to the temperature that is around the reaction. That's where our thermochemistry stuff comes in. So when those things happen, when things get added or the pressure or temperature changes or whatever, the dynamic equilibrium will shift to compensate for those changes. So I want you to think about a reaction in equilibrium to look a little bit like this. It's like a balanced teeter-totter. And the reactants and products they don't have to be matched in terms of their masses or anything like that, but just this is trying to demonstrate that the rate of forward reaction is the same as the rate of the backwards reaction. Okay, so that's what this teeter-totter is going to symbolize. We'll see that a lot here. Okay, so stress is something that will tip the balance, and then a shift is something that reestablishes the balance. And so we're going to use the word stress and shift here quite a bit. So let's just say that we stress the product's side of the reaction. So the side of the reaction that gets stressed, I want you to picture the teeter-totter falling down on that side. Okay, and in order to reestablish the equilibrium, we say that the reaction will shift to the reactant's side. So we have a shift to the left is what we call this. Okay. And then vice versa, if we stress the reactant side, we are tipping the balance, which was formerly balanced. We're going to tip that toward the reactants, and that's going to cause a shift toward the products in order to reestablish the equilibrium. Okay, so let's talk about each individual stress one at a time. The first one we'll start with is changes to the amount of reactants and products. So in a closed system, we're not adding any new stuff or taking stuff away, but once we start doing that, we stress the equilibrium. So picture our reversible reaction in dynamic equilibrium here, and let's add reactant. Okay, and so when we add reactant to the balance here, it tips it toward the reactant side, which then prompts a shift to the right in order to reestablish the balance. And really it just gives you more reactant with which then you can make more product. Okay, so that's the shifting to the right when you add more reactant. If we add more product, the opposite thing is going to happen. So if somehow we introduce more of the stuff that's getting created in the reaction, then the product side is stressed, and then we need to shift to the left in order to reestablish our equilibrium. Okay, when concentration increases, and concentration, we just, sometimes when we say the amount of something, another way to say that is concentration. So when the concentration increases, the equilibrium will just shift to the opposite side of the reaction. That's the rule of thumb. Okay, and then we can also decrease some of these things as well. So let's just say that we take reactant away from the mix here, and so think about reactant getting sort of moved away, and that causes the teeter-totter to fall toward the product side, which will prompt a shift to the left in order to reestablish that equilibrium. Okay, so we're stressing the products by decreasing the amount of reactant that is there. Okay, and we can do the same thing to the product side. So like here's our equilibrium, and if we take product away as it gets made, then we are in effect stressing the reactant side of the reaction, and we're going to prompt a shift to the right to make more product. That's important. That's actually the one that probably makes the most sense. Like if you're in the business of making a certain type of chemical that wants to revert back to its reactants, it probably makes sense to siphon off the product that you're making in order for the reactants to then continue to make that product. Anyway, when the concentration decreases, equilibrium shifts to the same side of that reaction. Okay, so let's move on to talking about changes in pressure and volumes. So these two kind of go hand in hand. There's an inverse relationship between pressure and volume. Remember when we talked about Boyle's law, that was the case. And so one thing to know about LeChatlier's principle and the dynamic equilibrium is that this one with pressure and volume only pertains to gaseous reactions. So all of the reactants and products are gases. Okay, so here's an example of that. We have nitrogen gas, hydrogen gas in this reversible reaction to make ammonia, which will then break back into nitrogen and hydrogen at equilibrium. So I want you to just picture the coefficients here, the 3 and the 2, and the imaginary 1 right here. Knowing how many moles of reactant and moles of product is important with looking at pressure and volume changes here in these reactions. Okay, so here's the reaction at its equilibrium, and let's just say that we increase the pressure in the system, and that is really the same as decreasing the volume. If pressure goes up, volume would go down. It's the same kind of idea. So it stresses the side of the reaction where there are more moles of gas. Okay, so what happens here is that if we were to increase the pressure, it would make the teeter-totter fall this way. We are stressing the side with more moles. There's 4 moles over here, only 2 over here, and that prompts a shift to the right. Okay, so it shifts toward the side with fewer moles. All right, decreasing pressure and increasing volume shifts toward the side with more moles. Okay, so here, if we decrease the pressure, we are tipping the teeter-totter in the direction of the 2 moles, and it will prompt a shift to the left. Okay, where there are more moles. All right, next stress we can talk about here is the changes in heat energy to a reaction in equilibrium. Okay, and so this is where our thermochemistry stuff kind of comes into play. And so we're going to use the same reaction because this is a thermochemical equation. There's actually heat produced in this process. There's a 2 here, and there is a 3 here. Okay, so again, we wanna think about a thermochemical equation. This is the delta H that's stated here, and we know it's an exothermic reaction because of that negative sign there. Another way to write an equation like this is to include that energy as a product. If it were an endothermic reaction, the energy would be on the reactant side, but this is an exothermic. So let's just think about how this works. energy is not really a product. It's not a substance, but we can think about it in those terms for this. All right, it's actually something that is produced, if you like, in a reaction like this. So again, if we increase the amount of product, we're going to tip the scale in this direction toward the product, right? And that will cause prompt a shift to the left to revert things back into reactants. And so, like, if you're in the business of making NH3, it probably is in your best interest to do this in a cold environment, because the warmer your environment is, the more likely it is for your product to revert back to a reactant. Okay. Now, if we take heat away, if we actually cool this off and we remove heat as it's being generated, then it stresses the system toward the reactants, which will then prompt a shift in the reaction toward the product to make more product. Okay, and that's why you might want to make your ammonia in a cold environment, so you just continually make it. All right, so LeChatlier's principle it's a tough one to understand, but hope this helps.